Okay, there we are. Well, welcome everyone. I hope your conference is going great so far. For the next hour here, we're going to talk about architecture all the way down. We're going to obviously explain what I mean by architecture all the way down, and then explore a little bit more detail into how we can go about practicing it. The concept for this talk is based on my book, Java Application Architecture. If you're interested, I'll be around the Pearson booth at around 6 o'clock this evening. Chat a little bit, whatnot, if you're interested in stopping by. So the agenda today, we're going to look at defining architecture. And the reason I like to define architecture as part of this session is to give us a kind of a benchmark to level set. I would guess that if I asked 10 different folks what their definition of software architecture was, I would probably get 10 different answers. Now, each of those answers might contain some common themes, but I do want a level set for the rest of the discussion. Then we're going to look at the goal of architecture. What is the goal of architecture? What do we try to accomplish when we architect software systems? Then we're going to look at the paradox surrounding software architecture, and then explore how architecture all the way down helps us overcome the paradox and achieve the goal of architecture. So, this talk is your silver bullet for the week, right? We're going to solve the nemesis, the dilemma surrounding how we go about architecting software systems. We'll see if that happens, huh? So, defining architecture. Well, I want to start out with a little bit of a story. There's this law called Dallow's Law. And Dallow's Law states that evolution is irreversible. That is, as an organism evolves, it cannot evolve into a state that was previously held by its ancestors. Well, if I translate this loosely, wood burns, eggs break, we can't unbreak eggs. Time kind of moves in a single direction, forward, not backwards. Well, what does this necessarily have to do with architecture? Well, I like to use it as a loose analogy, because I think a lot of times with architecture, we look at architecture as something that we define up front in the early phases of a project, but we don't take into consideration how our software architecture must evolve over time, the adaptability of that architecture. And I want you to keep this in mind as we walk through the discussion today. But first, what is architecture? What I've done here is I've gone out and I've gleaned from several different sources some fundamental definitions of architecture. And I've highlighted in red some of the components of these definitions that I feel are the focus, the emphasis. This is from the Rational Unified Process, the significant decisions about the organization, the structural elements, the composition of these elements into progressively larger subsystems. This is from Fowler, a definition from an article that he wrote quite a few years ago, actually. But in this definition, what I find interesting is that he incorporates this notion that the architecture is that the developers have a shared understanding of the system design. So I want you to keep that in mind here in a little bit, because it's this social aspect of architecture that's introduced in this definition. He also talks about the components, the interfaces, and how these components interact. Here's the ANSI IEEE standard definition. Again, components, relationships, and the principles governing its design and evolution, which I feel is a pretty significant aspect of software architecture. A TOGAF definition, the formal description of a system, detailed plan of the system at the component level. So as we can see, as we walk through each of these definitions, there are some common themes here. The components, the interfaces, the composition of those components into progressively larger software systems, the significance of those decisions that must be understood and assessed. So after examining these definitions, I come to the profound statement that architects architect architecture. And might seem a little silly, of course, but if we think about this, when we think about software architecture, Is architecture a thing? Is it the structure of the system? Or is architecture a process that we go through to arrive at the structure? And then, how do we communicate that software architecture to other developers and members of the team? Each of these different aspects, the social aspect, the process aspect, and the structural aspect of software architecture, each play a significant role in the ability of our architecture, of our system, to survive and adapt over time. When we make the decision is equally as important as the decision that we make. And it's fascinating that on a lot of software development projects, we spend considerable time early in the life cycle focusing on software architecture. Typically, when we think of architecture, we think of something that we do early in the life cycle. In addition to that, we oftentimes think of software architecture as the structure of the system, or the architectural qualities surrounding the software system. But when we think in terms of architectural agility, something that I don't feel we do a good job talking enough about and discussing in the Agile community, but when we do talk about architectural agility, what exactly are we talking about? Are we talking about the structure, or are we talking about the process? Because as an architect, if I adopt the Agile mantra that I am going to embrace change, I am going to embrace architectural change throughout the software development lifecycle. The fact that I am willing as an architect to embrace change is a far cry from actually having the ability to make change within the context of the system. Because I can tell you, there's been a lot of software systems where I've sat down to make some, what I would foresee as some pretty simple fundamental changes, and I have been absolutely scared to death. Scared to death that the change that I'm about to make is going to have a ripple effect that's going to break something somewhere else in the system. So in order to develop this adaptable architecture, this architecture that can evolve over time, where we focus on the social aspect, the process aspect, and the structural aspect, I really believe we need to take a different approach to how we go about architecting software today. And part of that approach is this idea that I call all the way down. So with that said, now that we've kind of level set what we mean by architecture, we've talked about some of the challenges that we encounter. Is architecture structure? Is it process? What is it? What I now want to look at is what is the goal of architecture? What do we try to do when we develop a software architecture? Well, I think fundamentally one of the things that we're trying to resolve when we devise our software architecture is we want to tame the complexity of the software. We want to design flexible systems, and we want to tame the complexity. Well, this is a study that was done over a number of years. Probably the most fascinating part of this study to me is that somebody actually went out there and counted every single line of code in the world. And after they did that, they arrived at the exact number of 120 billion. That's fascinating. They had so much fun doing it that in the year 2000 they went out and they did the same thing again. And what they discovered is that roughly the number of lines of code in the world doubled over that time period. They drew the conclusion that, yes, the number of lines of code doubles every 7 years. Some other interesting aspects of this study. 50% of development time is simply spent understanding your code. That is, I sit down to make a change, and I'm just trying to figure out, one, what this method does, and two, what is the impact of the change that I'm about to make. Now, certain practices help with that. Practices like test-driven development. We write unit tests, and it, to an extent, gives us the courage to make change. Because if we do break something, hopefully, the unit tests will identify that, and we can go fix it. The same study actually has shown that 90% of software cost is maintenance and evolution. That is, we develop a system, maybe 12, 18 months, whatnot, for the initial phase to delivery, however we do it. And from that point forward, the majority of cost associated with software is all around maintenance and evolution. But when you think in terms of how we go about maintaining software and how we go about managing the evolution of software, a lot of times we don't even manage it. A lot of times after we develop that initial version of the system, there is no future emphasis on software architecture. Architecture is something that we do early. But then once we design the architecture, once we develop that architecture, we're done. One of the reasons is because we view architecture as the important stuff. It's so important that we want to get all of this architecture stuff done earlier so that we bring this predictability into the development lifecycle that we enjoy so much. But when we add all these numbers up, when we look at what this study tells us, ultimately what this means is that over the course of the next 7 years, and obviously I can't count because that's only 5 years from now, but over the course of the next 7 years, not only will we double the amount of code that we've written over the past 7 years, but what that means is that we will have written more code over the next 7 years than all of the code ever written combined. Now that's a staggering amount of code. That's staggering to think about. And yes, I understand that with dynamic languages that are more concise, that maybe don't have the density of some of the traditional languages, that we could certainly argue this point. But look for a minute at the paradox of choice that often accompanies us as we develop software systems on the Java platform. How many people have asked, what's the best web framework to use? What's the best ORM framework to use? All of these decisions that oftentimes paralyze us to inaction. We see the same in the JavaScript land today. What JavaScript frameworks should I be using? All of these different choices paralyze us. But it's an example of the growth of code over a certain period of time. So I took a look at the Spring framework from version 0.9.1. Which was released around 2002, to 2.5. And what I found is that the number of lines of code grew from roughly 10,000 up around 70,000. Now, I highly doubt that when Rod sat down to write that first line of Spring framework code that he thought, this is going to be a framework that evolves over the course of the next 10 years. Well, maybe he did. But that roughly equivalent to a 500% increase in the size of that framework. And certainly there are issues that the initial developers of Spring faced that they had to deal with and then went away. And then there were other issues that surfaced in later versions of the Spring framework that there was absolutely no way they could anticipate back in 2002. A good example today of this type of challenge that we face is when I go talk to development teams. It seems that a lot of teams today want to know how they should go about making their web applications more consumable on a 3x4-inch display, a smartphone. And a lot of times, because we've developed these monolithic applications, that is not an easy thing to do. Yet, when they initially began developing those applications, back in, say, 2006, 2007 time frame, if they would have walked into a room and said, we need to design this application so that at some point it can be easily viewed on a 3x4-inch screen, folks probably would have looked at them like they were crazy. There is no way we were willing to make that investment back then. However, today, that's exactly what we want to do. Because when we look at internet traffic, a considerable share of traffic happens via smartphones and certainly tablets. So all of these changes that we face, they are not a bad thing, they are a good thing. It's a very good thing, because if our software didn't change, ultimately it would die. Nobody would use it. The fact that we have to constantly maintain our software and grow our systems over time mean people want to use it. People expect more from it. Layman's law, however, states that as we evolve software in this fashion, its complexity naturally increases unless work is done to actively maintain it or reduce it. That implies that we can't just focus on architecture up front. Instead, we really have to focus on architecture across the life of a system, across the development life cycle. Big architecture, big design up front are simply not going to work. They can't work because software evolves. And if you start with a system that's only 10,000 lines of code, and you devise the architecture for that software early up front, there is absolutely no way you can anticipate the change that that system is going to go through over the course of the next 5, 6, 7, 8, 9, 10 years. And the growth of that system as the number of lines of code increased by 500%. In addition to that, if you look at architecture up front, what I find absolutely fascinating about this is that we're actually asked to design solutions to problems that require knowledge we just don't know, we don't have. A typical software development project, what is the very first thing most of you know about any project that you're on? The date it needs to be done. We know we have to be done in 12 months from now, yet we don't know what we're supposed to be doing. If you really think about the absurdity of that, it's quite fascinating. How can we possibly be told when we're supposed to be done, yet we don't know what to build? How can we possibly devise our software architecture when we don't really even know what exactly the system must do? We don't really know where the greatest areas of risk necessarily lie. So we really have to shed that notion of big architecture up front. We have to architect throughout the life cycle. And ultimately, when I focus on the goal, or I ask what the goal of architecture is, it's actually quite simple. Architecture is about designing the flexible software that can adapt and evolve. And if that is what I want to do with my architecture, then the goal of that architecture must be to devise systems such that I minimize the impact and the cost of change. I have to find a way to minimize the impact and cost of change so that when I go in to make a change, it's relatively easy to do, or at least as easy as I can possibly make it. So, what if we were able to reduce the impact and cost of change? If we were able to do that, effectively what we've done, and now you're probably all going to gang up and try to throw me out of here, we need to eliminate architecture. In fact, this is an idea that, again, I draw upon Fowler, so I'll blame him. I guess he's not here right now, even though there's probably people here that know him. But in an article written by Fowler, Who Needs an Architect?, this is exactly the notion that he raises. That if we're able to reduce the impact and cost of change, well, effectively we've eliminated the architectural significance of change. So when we look at how we go about eliminating the architectural significance of change, what we have to recognize is that it's probably not possible in all situations. It's probably not possible to design a software system that is ultimately flexible, that can accommodate change. However, it is possible perhaps to look at different areas of the system and take a much more conscientious approach to the decisions that we make. lean software movement has this notion of reversible and irreversible decisions. Reversible decisions can be easily changed because the architecture is able to accommodate change. Irreversible decisions are not easily changed because they are expensive or resource intensive. Now, every software project has these type of decisions that we have to make. Every software project has decisions that we control, that we can say, this is going to be a reversible decision, this is going to be an irreversible decision. Think of some of the decisions you make, the decision to use hibernate, the decision to use spring, the decision to use struts, the decision to use any type of framework, how you go about structuring your system. If I want to make the decision to use hibernate a reversible decision, I can do that. I can do that by designing an extra layer of abstraction because, as we know, any problem can be solved by an additional layer of abstraction, right? But I can solve that issue by designing an additional layer of abstraction that decouples my application from the hibernate framework. I can do that if I want to. But I only want to do that if I have the need at some point in the future to replace hibernate with a different ORM framework. I can also say, I'm going to make this an irreversible decision. That is, if I decide to make using framework X, if I want to change framework X, it's going to be very costly and expensive to do. These are the decisions that we make. Now, what's interesting, though, is that as we approach software development, oftentimes we don't think in terms of reversible and irreversible decisions. Maybe subconsciously we do, maybe subconsciously we recognize that, but we don't frame it in those terms necessarily. But if we think in terms for a moment about the irreversible decisions that we have to make, the decisions that are going to be really difficult to change, at what point in the software development life cycle should I be making those decisions? Well, in general, traditionally, we try to make the important decisions early in the software development lifecycle. We try to make the important decisions before we have all the requisite knowledge that's going to allow us to make the most informed decision. Instead, what's possibly a better idea is to make as many of the reversible decisions, that is, the decisions that you can easily change early, and allow those to flesh out all of the risk and the unknown surrounding some of the irreversible decisions, and make the irreversible decisions at the least responsible moment, thereby ensuring that we have the most amount of knowledge possible when it comes time to make those decisions. Okay, so that brings us to the paradox. Because certainly it's going to be easy to make irreversible decisions because we just make the decision and we live with it. Those are the decisions that we have to live with. The decision to use Java, the decision to use Hibernate, the decision to use Spring can all be examples of irreversible decisions if we don't design the right layers of abstraction to ensure that we can rip and replace when we need to. But what about those reversible decisions? What about the areas of the system where we do want to ensure we have the most flexibility possible? In fact, this is one of the biggest issues with software architecture, is that we try to design these areas of the systems that have ultimate and flexibility that can be easily changed, that can be modified, and in reality what we actually accomplish is the exact opposite. And this is the paradox. I find several paradoxes associated with software development, and it's actually quite fascinating. Sometimes I think we do things a certain way just because that's the way it's always been done, and yet we never step back and actually question, why am I doing it that way? Well, a common example that I saw several years ago is organizations were trying to figure out this thing called iterative development. And they would have their requirements iteration, followed by their design iteration, followed by their construction iteration, and each iteration was roughly 3 months, and they only iterated through it one time. So, so they were basically putting a facade on top of waterfall. And then what they found is that, 3 months wasn't enough time to gather a stable set of requirements and get sign-off from my user. Because for some reason when we got into development, everything changed. So if 3 months wasn't enough time, you know what? Next time I'm going to spend 6 months to stabilize requirements. And I think over time we've definitely learned that that approach simply does not work. That predictive approach to software development does not work. And yet, I don't feel that we've done a good job taking those ideas and adopting them in how we go about architecting our software. So what is the paradox? Well, the paradox is that as we try to increase the evolution of our software system, what we ultimately oftentimes do is decrease the ability of our software system to survive. All of the flexibility that we're building into the software system, all of this flexibility that we're building in so that we can reuse different software entities, so that we can compose larger entities from smaller entities, so that we can extend the system with new functionality, so that our software that we develop is lightweight. That is, that the software isn't tightly coupled to any specific operating environment. All of these things that we do to increase the flexibility ultimately breed complexity. They make the software more difficult to understand. They make the system more difficult to maintain because they are more difficult to understand. And ultimately, anything that we create from a component standpoint is actually going to be more difficult to use. I always like to use the example of Log4j, but take a look at any framework that you use across a wide array of products. Very reusable, but as you use this, as you incorporate it into your project, there's oftentimes a lot of configuration that you need to implement in order to get that thing working in your specific environment. So this flexibility breeds complexity. And as Ralph Johnson states here, making everything easy to change makes the entire system very complex. Flexibility breeds complexity. As I try to create systems that can adapt, ultimately what I'm doing is I'm decreasing the ability of the system to survive. And I think we've all experienced this. This is what causes software to rot. This is what causes software to crumble from its own weight. We've all seen systems like this. This is why we oftentimes find ourselves in a situation where we have to rewrite the software system. It's because we architect something up front. We think we're designing flexibility where we need to design flexibility, but perhaps we're designing it in the wrong ways, in the wrong areas, and not ultimately giving ourselves the flexibility in the areas that we need it. I'll give you an example. I was working on a system a few years ago, and one of the developers decided that what they wanted to do was design a data access layer that allowed us to swap out the underlying database. So the organization that we were working for, we were using DB2, and the developer decided it would be a good idea if we designed a data access layer that we could swap out with Oracle if we wanted to. Well, if you looked at this organization, they had been using DB2 since the moment they wrote a single line of code. This was an organization that was very tightly tied to IBM, and there was no way they were ever going to move away from DB2. So ultimately what we were doing is we were trying to design the flexibility in an area where we didn't need the flexibility. Where we really needed the flexibility is the ability to load objects in different ways. Whether it be to load a complete object graph or to load a single object that consisted of many records. Those were the real problems that we had on this particular software. And so it took quite a bit of effort for us to persuade this individual that we didn't need the flexibility in the way he thought we needed it. So the key is that we have to recognize the areas of the system that demand the increased complexity that will bring greater flexibility. Well, this is not an easy thing to do. Because as I've mentioned, when we're designing that initial version of the system, we don't always know the interesting ways that folks are going to try using the software going forward. We don't necessarily know what future versions hold in store for us. It is why we can't do all of this up front. We have to do it over the course of time. We have to be willing to undergo the architectural refactoring, layman's law, to manage the complexity of the software over its lifetime. We have to be willing to undertake the architectural refactorings that are going to allow us to maintain that flexibility and ultimately ensure our software can adapt and evolve over time. And that brings me to architecture all the way down. Now, as I mentioned, this is the silver bullet that you've all been looking for. I say that jokingly, of course. This is one technique that we can use, and certainly if you were at my talk on Monday, my university session, you know that a significant part of this, I believe, has to do with software modularity. The fact that if we modularize our software, it gives us an additional way of looking at our system that we can't have without modularity. We simply cannot have it. It gives us a way to focus on specific areas of our system, and it gives us an answer as to where we need to design the flexibility. For example, which area of this system demands the most flexibility? How can I possibly tell? If this is my class diagram, and certainly there are probably, 10, 11 classes up there, this would be an incredibly simple software system in the real world. Incredibly simple. Most software that we develop has thousands of classes for any moderately large or moderately sized system. But even here, how do I know which areas of the system demand the flexibility? Where do I put my abstractions? Where do I put the concrete classes? How do I ensure that things aren't coupled too heavily? Incredibly difficult to tell. On the flip side, not at the class level, but I see a lot of organizations who adopt web services in the hopes that web services are going to solve some of the ailments that they've been experiencing surrounding system rot, reuse. Doesn't it seem like every single technology trend of the last several decades, not every single one, but objects, components, SOA, sold reuse as its saving grace? Reuse was the primary benefit of the object-oriented paradigm. That's what we were told in the 90s. Likewise with SOA. Reuse and SOA. SOA, reuse. Reuse your services. Well, we also like to say that SOA enables business agility, whatever the heck that means. But think about it. How agile is a web service if the stuff inside of it is nothing more than just a rotting design? Heard one guy laugh. But you see that a lot. You stick this pretty interface on top of this tremendous mess. It's like putting lipstick on a pig. Right? And we don't give ourselves the flexibility that we need. I've worked with teams where the only thing they focus on when they develop web services is the interface. So they're focusing on WSDLs and all that wonderful stuff, but they're not focusing on the implementation, the structure of the implementation, because your architecture is really only as good as the weakest line of code. It only takes one line of code to bring a system to its knees. And that's where I suggest that something is missing. Something is missing in between. We spend considerable amount of time designing our classes. We focus a bit on services and the relationships between services or applications or whatnot. But oftentimes we don't spend time designing our package structure, and we don't spend time designing our module structure, but each of these has significant benefits because they solve different types of problems. They solve different types of problems. And this brings me to the story of turtles all the way down, which I like to use as an analogy to architecture all the way down, where Bertrand Russell was giving a lecture at a university, and he talked about how the moon orbited around the earth and the earth around the sun, and at the end, a little old lady stood up in the back and said, "We all know that the earth is just supported on the back of a giant tortoise." And he replied, or asked her, "Well, what is the tortoise standing on?" And she said, "Oh, it's turtles all the way down." Well, we have to take that mentality with architecture as well. Architecture all the way down. We have to focus on architecture at multiple levels of abstraction within the software system, because it gives us so much information about the software system itself, from a structural standpoint, but also from the ability to communicate with other developers. For architects who may not live in the code, who might focus on the breadth of the system, we need mechanisms to communicate with them, and that's ultimately what architecture all the way down helps us do. And that's where I say software modularity plays a very, very important role in architecture all the way down, because it does give us a way to communicate with other individuals about the structure and the behavior of the software system. If I look at classes, classes are a unit of state. We have instance variables in classes. They're units of state. We instantiate objects. That's lowest level in our system, directly above the code. But then above classes, we've got packages. And I work with teams all the time who completely ignore the package structure of their software system. They decide how classes go in packages based upon the package that has the fewest classes already in it. Oh, this package only has 3 classes in it? Well, then I'm going to put this class there. That's the next bucket I'm going to fill up. And then when that one's full, I'll create a new package and I'll move on to the next one. No logical reason many times surrounding how we go about packaging, how we go about allocating classes to packages. And oftentimes, even if we do consciously allocate classes to packages, very few teams spend time on analyzing and dissecting and understanding the relationships between packages. How tightly coupled are packages? How loosely coupled are they? I like to pick on layering because many of us layer our application. Excuse me. Presentation layer, domain layer, data access layer, something to that effect. But a lot of times we only layer it according to the class structure. We have UI classes. We might have UI packages. We might have domain classes, maybe some domain packages, and data access. But what are we doing to actually enforce that our software system is layered? How do we know for certain that a developer didn't decide in the data access layer to import something from the UI layer? The only way that we can actually know that is if we enforce it and if we establish a set of constraints that people have to live by. And we can do that by architecting all the way down. We can run tests that validate our package structure. We can visualize our package structure. We can do the same with how we package our application into software modules. By only building what's absolutely necessary in the build class, only including what's absolutely necessary in the build class path of each of the individual layers. How do we go about reusing software? The reuse release equivalence principle. This is why objects failed so miserably at reuse. The unit of reuse is the unit of release. Objects are not the unit of reuse, are not the unit of release. Think in terms about how we reuse a piece of software. We go get something that's built and we include it in our class path, and then we reuse it. We use it. That's how we reuse software. Sure, objects provide some extensibility constructs that make it much more flexible, that allow us to perhaps configure it to context that can help some of the reusability aspects. But we don't actually deploy an individual object and reuse it. So when I ask people how many teams are actually designing all of these different aspects of software architecture, typically what I see is that most folks design class relationships. Just about everyone spends time on class design. Most people spend time, if you're developing web services, spend time on designing the relationships between services and the interface of the service. But from there, it drops off pretty sharply. From there, when I ask folks, how often do you design package relationships and manage the relationships between your packages? About 25%, and even fewer than that are designing the module relationships. Actively spending time determining what the granularity, the behavioral granularity and the relationships are between modules. And this stuff is not rocket science. But think for a moment about if you've not focused on modularity at all throughout the course of a large software system, and now you decide, you know what, now I'm going to modularize it. Because modularity on the Java platform is mostly about how we go about packaging the software into the respective modules. So now I'm going to focus on modularity. And I think that you need look no further than some of the challenges that Oracle has had with the Jigsaw module system. If you look at Jigsaw module system, started in 2007, and they've had difficulty modularizing the JDK. Why? Well, because we didn't focus on modularity throughout the life cycle. But there are significant benefits in doing so. The same with your software systems. It's more than just how you package it. There is a considerable amount of design energy that goes into creating a flexible and resilient module structure. So when I ask, where do you need the flexibility? You need the flexibility at the joints or the seams of your software system. That's really where we need the flexibility. The goal of the OO paradigm can be pretty easily summed up by the open-close principle. A system should be open for extension and closed to modification. That's pretty much what we can sum up the OO paradigm with the open-close principle. But think in terms of what it would take to design a piece of software that was so infinitesimally flexible that we could extend it by only writing new code, that is, implementing new abstractions, but never had to modify an existing line of code. Gosh, you'd have abstractions all over the place. Everything would be an abstraction. It would be so difficult to understand. So if we focus our energies at the joints, the seams of the system, that's where we need the flexibility. But in order to do that, we have to look at the system from multiple levels. We have to look at it not just at the class level, but also the package level and the module level to focus on the seams. Otherwise, we don't have seams. In fact, Booch talked about this idea several years ago in a book that he wrote, The Seams of the System. That's where we need the flexibility, because everything else is encapsulated. And at least we have the ability to isolate change. Not saying that design isn't important in other areas of the system, it is, but it's more important at the seams. Take an example. I actually drew this diagram. It took a while. As you can see down here in the bottom left, there is a little red rectangle. That is the class that is changing in this system. That's where the change needs to take place. how do I possibly know what the impact of that change is going to be across the rest of my software system? How can I possibly know? Well, it's a guess. It's a change it and let's see what happens. But as I modularize the system, or as I view this more from a module level than just a class level, it allows me to take a different view into the software. I've now modularized certain sets of classes, as you can see by the gray background, and highlighted in red the joints, the seams of the system, the interrelationships that exist between the modules. And as a result of that, I know that based on the relationships between the modules, the only modules that can change are those with dependencies on the class containing, or on the module containing the class that will change. Everything else is fine. The change has to be isolated, the ripple effect of change has to be isolated to the dependent modules. Now, that's not to say that if I do something stupid and change it and introduce a defect into the system, that I might not break the rest of my system. Certainly I can do that. I'm talking about the ripple effect. I make a logic change and somehow that doesn't work with something else somewhere in my system. Has to be confined to those in the top left quadrant. Has to be. That's what viewing the system at different levels gives me. Think about how we package software today. We spend all of this time on object-oriented design, conceptual design, but then oftentimes we take it and we just put it into this one big deployable unit called a war or an ear file, and boom, shoot it up on a server. So all of the extensibility benefits that we hope to gain, all of the maintainability benefits that we hope to gain from designing a flexible software system, I've got a system of 500,000 lines of code. I spent considerable time and energy designing a software system with a flexible class structure, yet if I change a single line of code, I've got to recompile the whole thing and redeploy the whole thing. Well, that seems kind of silly to me that I would recompile all 500,000 lines and redeploy everything simply because I made a single change. But that's oftentimes what we do. But as we modularize our software system, not only does it give us the ability to independently manage specific modules, not just at development time but runtime, but it also offers us a world of flexibility surrounding how we can go about reusing different modules across software systems. Again, think in terms about how you reuse. When you reuse something, you have to reuse the unit of deployment unless you're reusing something already within the software system or within the application. Either that or you invoke a web service. Here, now we have a new form of reuse where if the service doesn't do what I need it to do, I can just compose a new service from the existing modules that give me what I need. And there's many different ways that I can go about doing that if I have a modular architecture. Here's exactly what I'm talking about. I've got some web service, call it bill pay. This bill pay service, instead of internal design of this bill pay service that's just a jumble of classes, I've focused on modularizing it so that there's not a rotting design that's sitting inside this service. As some process comes along, it can either reuse the service, RESTful web service, whatnot, or if the service isn't at the right level of granularity, which is one of the biggest challenges with reuse anyway, especially as we try to reuse business functionality, the level of granularity. How many times have you wanted to reuse something only to find that it does a little bit too much for what you need? And so you can't reuse it. Instead, you copy it and paste it, and you strip out the stuff you don't need. As we have these multiple levels within the system, architecture all the way down, we can jump in at the right level at which we need to reuse something. And here, if I have a new process where this bill pay service does just a little bit too much for me, it's not at the right level of granularity, I can compose, going back to the definition of architecture, I can compose a new service from my pre-existing modules. And if the modules don't necessarily do what I need, if those aren't at the right level of granularity, I can move down into my package structure and look at the set of packages that I need. And maybe change the build script, adjust that accordingly to do a bit of refactoring of the modules to give me what I need. But if I don't architect all the way down, I don't have any of this flexibility. There is no way that I can. In addition to that, if I look at how architects oftentimes communicate to developers, a lot of times which I see as being a very disjointed process, a very disjointed communication channel, simply because they view the system at two completely different levels of abstraction. Developers live in the code, architects live up in the tower. They don't see eye to eye at all. The architects think they've got a system that looks like this. The developers have gone off in their own direction because they knew that the stuff the architect gave them wasn't going to work. As I use these additional levels in my system, it gives us another mechanism through which to communicate. Classes, packages, modules, all the way up. It gives me multiple levels to communicate my architecture and to help me understand the software system. So where to now? Where to with this stuff? Well, certainly there are modular frameworks available for the Java platform. Jigsaw is under development by Oracle. There's OSGI today. But those offer support for modularity. Those provide a runtime environment for modularity. But think in terms of the object-oriented paradigm. The fact that Java supports fundamental OO constructs, inheritance, dynamic binding, polymorphism. When we learned Java, we did not have a difficult time understanding how to use the extends keyword or how to use the implements keyword. We didn't have a difficult time with that. We didn't necessarily have a difficult time understanding how dynamic binding worked. The real difficulty was the design paradigm, how we went about applying those concepts to design flexible software systems. That is something that a runtime framework, a module framework, is never going to help us with. They simply allow us to create a mess of a different color if we don't use proven design techniques. So the design paradigm, focusing on granularity, the weight of a module, and how we go about designing a modular software system. And I fundamentally believe that as we move forward and we continue to develop software as software needs to adapt and evolve over its life, that we need to spend time focusing on modularity and how we go about designing these large-scale systems that do have the ability to adapt and evolve. So with that said, I'd like to thank you all for showing up today, and I hope you have a great rest of your conference. Thank you.